An eccentric but wealthy investor has a flying saucer, and the flying saucer's data has been recorded, and our job is to come up with a mathematical model that will predict the height of the flying saucer at a certain time. In this part, I am importing pandas and using pandas to read a CSV file, and then I am getting some information, and then I cast the information in the CSV file into a data frame. And looking in my data frame, I see that there's a time column and a height column. There are 800 entries in each column. And then I decided to store these into two different things. So the time column I put into a new variable called time data, and the height column I put into a new variable called height data. Then I imported matplotlib.pyplot as PLT. And this block of code is showing the position. Remember, we said it looks a little curved, but it looks pretty linear also, just from eyeballing it. Then when we looked at the correlation coefficient is extremely high. Correlation coefficient is a number between -1 and 1, and if it's +1, that means that you have a perfect positive linear relationship. So this number being so close to 1 says that's another indicator that we have a good linear fit. To avoid overfitting on the training data, to avoid overfitting to the data we have, one common technique is to split the data into a training set and a test set. And we're going to fit the data, we're going to fit the model on the training set, then use the test set to make sure we didn't overfit. Here I am importing my train test split command from sklearn model selection, and I'm importing linear regression from sklearn linear model. And this block of code, so I'm using the train test split function along with a couple of different arguments. The first is the input data, which in this case is the time data. The second argument is the output data, the height data, and then what proportion of the data that I have do I want to pull into training. And it actually spits out 4 things. It's going to spit out a training input set, a test input set, a training output set, and a test output set. And we can go over a little bit more about how that works, but for now, it's enough that you understand what's happening as the end result. The first thing we will do is create a linear regression object. So I do lm linear regression, and then I'm going to fit the linear regression only on the training data. So it should be lm fit ttrain, height train. I might have made this mistake in class. It should be train, not test. So I'm fitting on the training data, ttrain and height train. And I want to know how well it fit the training data. So I can use the score method, which gives me the r² coefficient of determination. Now remember, r² is just literally the r value squared. And so r² takes values between 0 and 1. It tells how well the proposed model fits the data. So when we have a value of r² for this linear model on this training data of 0.99, that's an excellent fit. That's very good. And so the way that we check, we use our test data, and we get the r² value of this model on the test data as well, and the fit is excellent there as well. So we have 2 indicators that this is pretty good. The first is that the data looked roughly linear in the scatter plot. The second is that the r² values are high for both the training data and the test data. Process of fitting the linear model to our data, things looked good so far. But we should be careful. There are some plots we should make to look at this. And the first one is we can plot our original scatter plot versus our line of best fit. So in order to do that, we're going to use the lm.predict function. And what predict does is it takes the linear model lm that we fit here, and it uses it to make prediction on a set of numbers. Now here I'm using it to predict it on the original data that we had. You can use it to predict on anything that would make sense to plug in. So I'm going to use that though to create all the prediction. And then what I'm doing in this code is first I'm creating a scatter plot of the original data, and then I'm creating a line plot of my time data against my predicted height data from the. So that's this that I just created, and I'm doing some things with labeling and coloring and changing the x-axis and y-axis a little bit. This plt.legend is necessary to see the labels, but at the end of it, you see here is the regression line that we made, and here is the actual height. And I see a problem. if you look from 0 to about 1.5, the line is entirely above the curve. And then from about x equals 1.5 to x equals 5, then the line is entirely below the curve. And then finally, past that, the line is again above the curve, and that's worrisome. You wouldn't want to be able to predict whether the line was above or below the scatter plot based just on information. So this long stretch of above, below, above, that lets me know there might be a problem with my linear model. And the next thing I want to look at then is what are called the residuals. So the residuals are the difference between the observed value and the predicted value. So because I created this HT pred a minute ago, that predicted the height or all of the time data that I had. So I can create the residuals by, I'll say height residuals equals height data, which was my actual data, minus height pred, which is the predictions that the model would have made on these inputs. Again, it's observed minus predicted. Did I not call this HT data? I called it height data. Next time, let's use shorter variable names that still manage to convey what the information is. So height data minus HT pred. Make sure we spell it correctly. Cool. Okay. So I think it's worth looking at height residuals here. Let's look at height residuals. It's a long column, so what I'm doing here is I have two columns of numbers. I have one that was height data that I created way back at the very beginning from my data frame. Height data is a column from the data frame. And then I have this HT pred, the predicted height, in other words, which are the corresponding predictions that the model made on the time data. So these both line up with time data, and this is the actual, and this is the, so this is the actual, and this is the predicted. And now I've created the residuals. And what I want to do is plot the residuals against first the time data. So plot the residuals against the time input data. And I'm going to say plt.scatter time data residuals, and let's make the size not too big. And I'm not going to do a lot with I'll just do plt.show. Okay, this is what my residual plot looks like. Basically, this is showing me the error against the time data. And this is terrible. Maybe do plt.grid true. That's helpful. But this is terrible. This is showing me that there's a clear pattern in my residuals. And that's not good. That means there's something that I'm missing. There's an error that is a consistent patterned error. I want the residuals to be noise if this is a good model.